Hello everyone, welcome to DevOps Info channel. Today we are going to talk about one of the most trending topic, which is the eBPF, that stands for Extended Berkeley Packet Filter. Let's proceed on more discussing about this topic. So let's talk a little bit about how the security has been present in any organization since last 10 years. If you talk about a decade ago, like every application, service, and data was present within your data center, and then you had a classic approach, like wherein, like, in order to consume your services data, you need to establish a VPN connection, and then you'll be able to consume the service. So basically, without VPN, you won't be able to consume your data, and most of the cases, your services and applications were not exposed to the internet. So that's the case, which was like 10 years back. And post COVID, and also during COVID, we saw a lot of applications were moved to the cloud, and also we started consuming a lot of the SaaS applications. For example, Microsoft Teams, OneDrive, SharePoint Online. These are the SaaS applications offered from the Microsoft. So as a result of that, your data is not present only in your data center, and also a lot of organizations started moving their application towards the Microsoft Cloud and other services because of utilizing the new features and the security enforcements that's coming from the cloud providers. So as a result of that, we have to take the approach of the zero trust, wherein, like, you need to protect assets anywhere with a central policy. We also talked about the zero trust in the previous video. I highly recommend to having a look at it if you want to have more deep dive and understanding of the zero trust. But if you talk about the common, the goal of the zero trust is to basically limit the blast radius, verify the identity, verify the device, do the continuous verification, least privilege access. You can have any one of these controls and grant access. So it's a possibility of having all the controls. That's going to be a big challenge, or having picking few controls which is required to maintain the zero trust in your environment. So of course, zero trust is provided by a lot of cloud providers like conditional access from Microsoft, and Google has this own zero trust policies. So it's whatever different kind of offerings, but they more or less follow the same approach to implement the zero trust in an environment. But the question is this zero trust is only sufficient enough to protect your environment? Let's talk a little bit about the operating system model. So if you talk about the past 5 decades, we have seen different flavors of operating system, with which Windows being the most dominant, used by most of the consumers, followed by Mac, and then few flavors of Linux and the Android operating system. Though we have different flavors of operating system, but you see, like, they follow the same dominant operating system model, which is like they have a user layer. On the user layer, you have the application and process, which is initiated. The process could be initiated by an application, or the process could be initiated by the user. So as a result of this, this process has to initiate a system call to the kernel. As we know, the kernel is the logical unit of the operating system, where it acts as an intermediate between the user layer and the physical layer. So whatever the process that's been initiated from the application layer, which is like the user, or the application that's coming from the user layer, this process needs to initiate with the kernel for any kind of operations. So let's say, for example, you want to start a process that's required to interact with the CPU. And for example, if you want to read a file, write a file, that's required to interact with your hard disk. And also, for example, if you want to do a communication externally, then you need to communicate with the NIC driver. So basically, in this case, the user layer, whatever this a user call, or it's the process that's coming from the application, these are coming as a system call to the kernel, and the kernel is interacting with the underlying physical components, which is the hard disk, memory, CPU, and the NIC drivers. So looking into this, do you really think having only the zero trust is going to protect your environment? The answer is no, because a recent analysis of the security, especially for the network policies, they say you need to definitely have you know effective solutions like EDR, which is like endpoint detection response, where you would be able to identify the the kind of actions that's happening on the operating system level, that's happening on the kernel level. And also that's the reason you also have the next gen firewall mostly present in the market right now, because the next gen firewall, they would be able to identify these kind of system calls, and they would be able to see whether it is a legitimate request that's coming from the application process user, or if it is a kind of an anonymous activity that's not triggered by a application or an end user. So what is the benefit of doing this? Because the moment when you started controlling, especially on the kernel space, you're first efficiently improving the process of the network flow. In this case, for example, we're talking about network, you can efficiently improve the process of the network flow. And two, you will be able to have a detailed insights about like what's happening, and the trigger is coming from which place, and who has actually triggered it. Like that, there could be a scenario like where a user accidentally downloads a file, and that file has a malicious trojan or a malware. And then the moment when the user clicks on it, obviously that's going to initiate a system call which is not initiated from the end user. And of course that's definitely going to affect, or bring a uh, malicious task to your environment. So that's the reason you need to always have a detailed level of insights into your, the end user level. That's the reason the EDR solutions came into the market. Like for example, if you talk about the Microsoft EDR, you have the CrowdStrike. So all these EDR solutions came into the market, and they are working in this eBPF layer. So having said that, let's talk a little bit about eBPF. So what's the eBPF? So the eBPF is something not new, which is introduced in the market. It's been there since 1992, which is initially it was introduced as a Berkeley packet filter. So this Berkeley packet filter is there since 1992. It was basically introduced to analyze and filter the network traffic. So the name Berkeley came is because it was introduced in the California University, in the California lab. So that's the reason, California University lab, Berkeley lab, and that's the reason it came Berkeley packet filter. And later, what happened? Like the evolution to eBPF came by adding more enhancements to the Berkeley packet filter, and that became as extended Berkeley packet filter. So, what is the improvements on this extended Berkeley packet filter? You'll be able to register all the kernel events. Like for example, then it's not only the network, you'll be able to register for the disk, process, thread, and CPU, because all these activities on the kernel happens as events. So this eBPF, with the eBPF, you'll be able to register as a kernel hooks from the eBPF application, so that you'll be able to identify like if the request is coming from the actual user, and you'll be able to have the observability of the task that's happening. Let's talk about a DDoS attack. For example, if you talk about a DDoS attack, uh, if you have this eBPF solution, the DDoS, it would be able to detect the DDoS attack exactly right in the process. For example, if you talk about the Linux system, any kind of network activities that's going to happen will first initiate in the XDP path, which is the express data path. So all kind of activities, especially on the eBPF that you have registered, is going to happen on the XDP path. So as a result of that, the eBPF solution is going to check if the request is coming from the actual user, or it is coming from any anonymous activity. Then it is going to drop the packet right away in the XDP path. So it's not even communicating this information to the kernel, and no further processing to your physical components. A NIC driver or a virtual NIC is happening, uh, uh, or even a physical NIC is happening. So as a result of that, you're efficiently improving the performance of your packet processing, and also you get a better insights and visibility. So that's the reason a combination of a zero trust and eBPF is always considered as a very good solution in any environment. So that's the reason we have the EDR, we have the next gen firewall, which is coming up a lot, and all these solutions are utilizing the eBPF. And for example, if you talk about the Catron, that's one of the load balancer that's developed by Facebook, and they developed this load balancer to balance the traffic efficiently for all the requests that's coming for them. So as a result of that, they found this to be very successful. And of course, this Catron is built in backend of the eBPF, and then this Catron load balancer is given as a outsourced to the community. And a lot of companies have also utilizing the this Catron load balancer and effectively utilizing, which is built on which is using the eBPF platform. And also, let's talk about the Cilium. Cilium is one of the CNI, the Kubernetes native, the benchmarking platform. So the Cilium, Sonic, the Azure Kubernetes service, everything is using eBPF. So the reason being why is with the Cilium, you'll be able to get a detailed insights. You'll be able to do the better segregation, which is very complex usually with the microservices because you have only the namespace. There's a separate slide which we'll talk more about it in few minutes. So basically, with this eBPF, you'll be able to do a high performance packet processing. You'll have a better visibility on your network, and then you'll be able to register to any kernel events, or you'll be able to modify, filter the network packets based on the kernel events that you have registered to the eBPF program. So going further, we talked about eBPF and how to build it and what is the value. How to build it is very simple. Uh, it's of course building is not simple. There are a lot of commercial off the shelf application. For example, Cilium, Falcon, all these are the commercial off the shelf application. You will be able to purchase them and then you'll be able to utilize them. And then basically they are going to sit as a eBPF program and they'll be able to register the kernel events and you can use it in your environment. The value is already be discussed because you would be getting a better insights and then you would efficiently improve the performance of your overall environment because everything is running as a virtual memory in the inside the kernel in a sandbox environment. And if you want to build it, for example, if you have a strong development team who is capable of doing that, then basically you need to build a user layer. In the user layer, there would be an application sitting on the user layer, and then you would have the kernel layer, which is the kernel space. So basically, this eBPF operates in two modes, which is the user layer, in which you would be able to perform the dynamic updates, and there is a kernel space. In the kernel space, it would be registering to the kernel events and controlling all the kernel registries that kernel hooks that you have done through this eBPF program. So based on this, the processors, memory, network, for example, if you have a list of block type is which you're dynamically updating from the user application layer, then those IPs would be present in the kernel space. Whenever a new packet is arriving, it would verify that, and the moment only when it is present, it's going to allow. So that's the overall idea of the eBPF. Let's talk a little bit more. So this is of course the slide which is taken from the eBPF website itself. So in the traditional method, you see like an application developer wants to develop a new feature in the app, which is heavily dependent on the kernel. Let's talk about they are improving a security feature or they are improving the performance, which is heavily dependent on the kernel. So they have to basically convince the entire community for this to accepted by the from their side. This is a huge change, right? Because for example, if you talk about Linux, they have 30 millions of code, which is like just for modifying for one feature update for an application or for a security enhancement or a performance improvement. Just modifying the kernel is going to take quite a lot of time because you're just modifying the operating system kernel. So that's the reason it's a quite intensive process, and as a result of that the requirement gets changed because it's a time delaying process. Even for example, if you talk about the Linux, they usually maintain the IP tables, because maintaining the IP tables is very important in Linux, for the network part. And of course, every process, as a result of maintaining the IP tables in the Linux, every rule that is traveling to the CPU is very intensive. For example, let's talk about a little bit about how the network evolution has been in the past and right now. Previously, you have all the networks controlled in the the transport layer. For example, you have a source, you have a destination, and then you're controlling with a set of set of rules, and then you say, okay, if the destination is going to be an application, and then it's the code is going to be this, I'm going to allow it. If it is going to be uh, and I if it is going to be a particular protocol, and if the destination is going to be some a critical application, I'm not going to allow. These are the examples. And then later we move to the application aware load balancer, where you'll be able to control all these things with the HTTP header response, and then post, get, all these things. They were application aware load balancer. But if you talk about even the layer 7 load balancer and also this layer 4, they were more CPU intensive, because everything at the end is coming to the NIC driver. It's coming to the virtual NIC, or it's coming to the physical NIC. Everything is processing through the kernel and the physical components, which is consuming a lot of CPU, as well as it requires more amount of memory as well. So, as a result of this, this traditional method is taking quite a long time, and also it really needs a lot of things to consider before making any changes on the kernel level in the operating system. But what is the new way with the eBPF? With the eBPF, like basically you're providing two kind of kernels, two kind of interfaces. One is the user space, and the second one is the kernel space. So the user space, you are giving an application where the kernel developer or your engineers will be able to do the just-in-time compilation. Like they will be able to make the changes, and then they are just pushing this as a mini programs from the user space into the kernel. So as a result of this, you don't need to make any major kernel level code changes. So this is effectively allowing the dynamic updates. So as a result of this, there is reduced latency, and you no need to switch a lot between the user and the kernel space, because the dynamic updates are performed based on the program which is running in the user space, and the kernel space, like eh, receiving the updates, and it's able to handle all those kernel events. So, with the new way with the eBPF, you don't need to convince the community as a whole to make any changes on the kernel level in the operating system, and then you will be able to dynamically push from the eBPF program, which is running in the top of the user layer. Let's talk a little bit about how to build programs for the various use case. Let's talk about like in reality, when you're having an eBPF program, or your team is developing the eBPF program. Let's say for a network, then there would be a user application where would be sitting on the user space, that would initiate a system call, and that system call is basically registering to the kernel events, and the eBPF program would sit right in between the kernel, and the eBPF program would sit in between the kernel and the physical layer. So basically, the syscall, whatever it's coming in, is first passed through the eBPF program. It doesn't even go through the kernel. First, it comes to the eBPF program, and the eBPF program is checking for the conditions, whether these kind of system calls are allowed to pass to the kernel, or I have to drop it. So in this case, the eBPF decides, because everything is happening in the XGP, the express data path. So as I said, like for the network, let's talk about the connection coming first goes to the express data path, and there this eBPF sits exactly over, and then it is checking whether it's able to route the traffic. It is able to it needs to inspect it, it needs to block it. So as a result of that, it's not even disturbing the kernel. As a result of that, like you're efficiently processing this the packets. There has been proven histories of the eBPF solutions delivering a fast packet processing when compared to the the traditional load balancers stuff. There is also a lot of articles in the internet. You can have a look at it. So that's the reason it's it's never interacting into the physical layer hardware devices. Let's talk a little bit about an example of a packet filter. Uh, let's talk about a packet filter, how the eBPF program handles. For example, if you are building it for a network, you see it on the right side. You have the Java-based eBPF application, which is present on the user layer, and then basically the user is able to give a dynamic updates to the eBPF program, which sits in the kernel layer. So what are the dynamic updates the user is sending? Like for example, they are sending the blocked IPs, and then the eBPF program is also sending the statistics to the Java-based eBPF application, which is sitting in the user layer. So let's talk about a real-time scenario when where the like where a real connection is coming from the internet. When the connection comes to the internet, first it hits the network driver. In our case, it's hitting the network driver. So what it's going to do is it's not going to send to the network stack. And by the way, for any network processing on the Linux, it initiates a various system code. Like for the Windows, it does the NDIS, and for the Linux, it initiates a various system code. So before sending it to the Linux network stack, the network driver is going to check with the eBPF program, and it says if it is the blocked or the allowed IPs. Sorry, if it's only the block type is. If it's in this example, so if it is the block type is, it's going to drop the packet right away, and then it's not disturbing even the kernel, which is efficient packet processing for rest of the request that's coming. And if it is in the allowed, if it is not in the block type is, it is going to send it to the next network stack, and then it's going to go to the application, which is efficient packet processing, and you get a better observability in the network part. So some of the use case of the eBPF is like you would be able to do a tracing and profiling. You will be able to identify the performance bottlenecks, optimize the resource utilization. When you talk about the networking, it's a natural fit for all packet processing for all the network solution. And observability and monitoring, that's very important because you'll be able to collection in kernel aggregation of custom metrics, and then you'll be able to do a better security auditing. You will be able to inspect all the traffic, and then you can take decisions based on the traffic that's been received. And then load balancing, high performance load balancing for network observability. We already talked about the cut run load balancer from the Facebook, one of the classics. So little bit more into the networking, how it works. For example, if you talk about if you talk about for example for the network, for the physical network, there are a lot of NIC cards that supports loading the eBPF into the physical NIC itself. So doing this, like you have eBPF program that's loaded into the physical NIC, and then it's connected to the physical network, and it would be able to pass, drop, manipulate, or redirect the packets. And we're coming to talk about the virtual NIC. Yes, you have the kernel, and then you should have you should have a network driver that supports the XDP, and then basically with that, the eBPF program sits exactly in the network stack, and it's able to do all the all the tasks on the kernel events that you're registering through the eBPF program. So what you can do more with the eBPF, first you could take action on the network packets. For example, a network connection is coming in, that's first into the raw circuit, and then you can do the queue disciplines for egress and ingress traffic. For example, you can set up the first in first out, you can set the priority, you can manipulate all these things with the queuing disciplines. And then you'll be able to filter the type of traffic, for example TCP, UDP, ICMP connection, and you'll be able to filter and then route it based on your requirement. And then of course it enables efficiency and high performance because everything is you're doing it in the kernel level, and you know you're a little bit compromising the kernel memory, but however it is highly efficient when compared to the traditional load balancers, how it operates currently. Having said that, let's go into the microservices. Currently, All the microservices are heavily using the eBPF for the CNI benchmarking, because if you talk about the microservices, they are basically application code running in the pods. They have their own network namespace. They're separate from the host namespace. They have a separate TCP/IP stack. So with this, like, you'll be able to do the fine-grained security policies, you'll be able to do the better segregation, and then you'll be also able to do the better efficient resource utilization. That's a very important thing. And last but not the least, you'll also be able to do the dynamic updates, which is really good, right? So this is also, a slide that's taken from the eBPF website itself. So basically, if you talk about the state of the eBPF, like, we're not going to change with the ABPF. We're not going to change any you know uh, codes on the kernel level. We are giving an option to the engineers where they can build custom programs and then they can push it in the kernel. And when talking about the clouds, most of the cloud, they are using the eBPF, as we talked about. Google, Meta, and also Netflix is using their leverage PBPF in their data centers for years. And one more thing to notify you, even for the open community, the Google, Meta, Netflix, they are also supporting to improve this eBPF program. And many applications already using eBPF. For example, the EDR solutions, and also the next gen firewall, they're utilizing eBPF quite a lot. There are some challenges to eBPF because you need the kernel expertise to write the programs, because also there is a risk associated coming with it. Because let's talk about, some accidental changes, or some chaotic updates that's been done on the kernel. Then it is going to bring a lot of challenges into an environment. So it's very careful when you're implementing this, and you need to have the right kernel expertise to do this kind of changes. So this is the transformation you see. Let's talk a little bit about even the Windows. Windows is also having an open source community program for improving the eBPF, which has been active since Windows 10 and Windows Server 2016. So because they basically have like tool chains, for example clang, that is eBPF tool chains clang, that you'll be able to do the modifications on this open source. So they're developing basically, the key idea for them is to make this eBPF program work on unmodified Windows components, open source eBPF for Windows, and open source other projects. So still it is in development, but it's not to the level of how it is currently for the microservices and the Linux platforms. So if you talk about the transformation, earlier we were heavily dependent on the data center, like where there would be hardware appliance. The challenges like scalability and expensive. And then we moved to the virtualization, where we had the hypervisor, and then security backup was a challenge. And now we are in multi-cloud, where we also get this eBPF offerings, where the challenge is like we need the kernel expertise to work on this. That's the most important part, because uh, without that, it is going to be a challenge. So for me, the future outlook is a combination of zero trust and the eBPF, because the primary focus is, for example, if you talk about the zero trust, you have the identity and access management. In the eBPF, you have the performance, security, observability within the kernel. And then if you talk about the administration, you have a easier and more adaptable in the modern world. Like zero trust is not that complex. Like you'll be uh, any any experienced person will be able to implement it with with some logic, and then takes some time. Of course, it's not easier, but it takes some time to understand and then implement. But when we compare about eBPF, it's easy with commercial off-the-shelf application. But if you're talking about any customization based on your environment application, then of course you need a kernel expertise with the development experience to go ahead with it. Also talking about the disadvantages, for example, the zero trust can bring false positives and other things mentioned in the column, and the eBPF can also bring security risk if it's improperly configured and it's limited to Linux. Thanks a lot for watching this video, and hope this helped you, and this helped you knowing about the eBPF. And Have a great day.